Hello there and welcome, where profound questions become gentle companions for the night. Tonight we're embarking on perhaps the most mind-bending journey we could possibly take together, exploring the possibility that everything you know, everything you touch, everything you feel might be nothing more than sophisticated code running on some unimaginably vast cosmic computer. Before we dive headfirst into this digital rabbit hole that philosophers, physicists, and computer scientists are seriously contemplating, I'd love to know where in the world you're watching from tonight and what reality feels like to you right now. Are you tucked into bed with the glow of your screen painting gentle shadows on the wall? Are you settling into a favorite chair as the day winds down? Whatever corner of existence you're occupying, I'm grateful you've chosen to spend this quiet moment exploring one of the strangest questions our species has ever dared to ask. And I do hope this isn't so fascinating that it keeps you wide awake. Though if it does, well, at least you'll have spent the evening considering whether you might be living inside the most elaborate video game ever created. So settle in, slow your breathing, and let's begin this gentle exploration of a question that sounds like science fiction, but has become serious science fact. Because somewhere between the pixels on your screen and the neurons in your brain, between the quantum fields that might compose reality and the algorithms that might simulate it, lies one of the most startling possibilities humanity has ever entertained. That we might all be characters in someone else's dream, bits and bytes masquerading as flesh and bone, living out our entire lives without ever knowing we're digital. The simulation hypothesis, as philosophers call it, suggests that what we experience as the universe, complete with its galaxies and gravity, its chemistry and consciousness, its love and loss and laughter, could be an incredibly sophisticated virtual reality. We would be simulated beings living simulated lives, our thoughts arising not from biological brains but from computational processes we could never directly observe. Every memory you have, every sensation you feel, every relationship you cherish, every moment of joy or sorrow could be the product of information processing rather than physical interaction. Your entire biography might be nothing more than data flowing through circuits we cannot imagine. This isn't the fevered imagination of science fiction writers, though they've certainly explored these themes with relish. This is a hypothesis that serious academics debate in peer-reviewed journals, that technologists consider when thinking about the future of computing, that physicists ponder when trying to understand the deepest nature of reality. The simulation hypothesis has crept from the margins of philosophy into mainstream scientific discourse because, as our own computational abilities grow exponentially, the idea that consciousness and reality itself might be computational phenomena has become increasingly plausible. Think about how far we've come in just a few decades. The computer that first put humans on the moon had less processing power than the device you're likely watching this on right now. Video games that once consisted of simple blips moving across primitive screens now create entire virtual worlds populated by characters with complex behaviors, realistic physics, and environments so detailed they can fool the eye. Virtual reality systems can trick our senses into believing we're walking through digital landscapes, touching objects that exist only as code, hearing sounds generated by algorithms rather than vibrating air. If we can create these convincing illusions with technology that fits in our pockets, what might be possible with computers thousands or millions of times more powerful? What if those future computers could simulate not just visual and auditory experiences, but every sense, every thought, every emotion? What if they could create virtual beings who believe themselves to be real, who experience genuine joy and suffering, who fall in love and dream dreams and wonder about their place in the cosmos, all while existing as patterns of information in some vast digital realm? This is the heart of the simulation hypothesis. The possibility that we are those virtual beings, that our entire universe is a simulation run by entities we cannot perceive for purposes we cannot fathom. It's a modern version of age-old philosophical questions about the nature of reality, dressed in the language of computer science and quantum mechanics. And as strange as it might sound, there are compelling reasons to take this possibility seriously. Look around you right now, wherever you are. Notice the light from your screen casting its gentle glow, perhaps the soft texture of your blanket or pillow, the familiar weight of your own body settling into comfortable rest. Listen to the sound of your own breathing, steady and rhythmic, the subtle creaks and whispers of your environment. Feel the temperature of the air against your skin, the solid reality of whatever you're resting upon. All of this feels undeniably real, doesn't it? The richness of sensation, the continuity of experience, the simple fact that you exist as a conscious being observing and interacting with the world around you. Now imagine, just for a moment, that all of this is an illusion, not in some mystical or metaphorical sense, but literally an illusion created by incredibly sophisticated programming. Every photon of light your eyes detect, every molecule your nose recognizes as a familiar scent, every nerve impulse your brain interprets as touch or temperature, could be nothing more than data carefully crafted to create a seamless experience of existence. You would be a digital entity, your consciousness arising from computational processes rather than biological ones, living in a virtual environment so convincing that you never suspect its artificial nature. This possibility sounds like the stuff of dreams and nightmares, of philosophical thought experiments, designed to make us question our assumptions about reality. But it's become a legitimate area of scientific and philosophical inquiry, because our understanding of computation, consciousness, and the universe itself has evolved to the point where we can seriously consider such scenarios. The simulation hypothesis isn't just wild speculation anymore. It's a testable proposition that some of the world's leading thinkers believe deserves careful consideration. The core insight driving this hypothesis is surprisingly simple. If it becomes possible to create conscious beings through computation, and if those beings can themselves create simulations containing conscious entities, then simulated beings would vastly outnumber non-simulated ones. Think of it as a kind of digital demographics problem. If every advanced civilization eventually develops the ability to run detailed simulations of their past, their hypothetical futures, or alternative versions of reality, and if these simulations can contain billions or trillions of conscious entities, then the universe becomes populated primarily by simulated beings rather than biological ones. From a purely statistical perspective, this creates an unsettling possibility. You would be far more likely to be one of the simulated beings than one of the original biological ones. Just as there are more copies of a popular book than there are original manuscripts, there could be vastly more simulated conscious entities than naturally occurring ones. This line of reasoning suggests that unless something prevents advanced civilizations from creating such simulations, we should seriously consider the possibility that we're living in one. But what would it actually mean to be simulated? This question touches on some of the deepest mysteries in science and philosophy. We still don't fully understand how consciousness arises from the biological processes in our brains. We know that electrical and chemical signals flowing through networks of neurons somehow give rise to subjective experience, to the inner movie of thoughts and feelings that constitutes your mental life. But we don't know exactly how this happens, or whether the same kind of consciousness could arise from silicon and software instead of carbon and chemistry. If consciousness is substrate independent, if the pattern of information processing matters more than the physical medium in which it occurs, then digital minds could be just as real, just as capable of genuine experience, as biological ones. A simulated person wouldn't be a philosophical zombie, mechanically going through the motions of consciousness without any inner experience. They would have genuine thoughts, real emotions, authentic relationships, and meaningful experiences. The fact that their consciousness arises from computation rather than biology wouldn't make it any less real or valuable. This possibility is both fascinating and slightly unsettling. It suggests that the boundary between real and artificial, between natural and simulated, might be far blurrier than we typically imagine. If you discovered tomorrow that you were a simulated being, would your experiences up to this point become any less meaningful? Would your relationships feel less significant? Would your emotions seem less genuine? The simulation hypothesis forces us to consider whether the substrate of consciousness matters as much as we intuitively assume it does. Of course, we're still far from being able to create truly conscious simulations ourselves. Despite rapid advances in artificial intelligence and computer graphics, our current technology can only create pale shadows of genuine consciousness and realistic experience. The gap between today's most sophisticated simulations and the kind of comprehensive virtual reality that could house conscious beings remains enormous. But the trajectory of technological development suggests that this gap may not remain unbridgeable forever. Consider the exponential growth in computational power over the past several decades. The processing capability available to researchers and developers has increased by factors of millions, and this trend shows few signs of slowing. Meanwhile, our understanding of the brain and consciousness continues to deepen, potentially providing blueprints for creating artificial minds. If these trends continue, future civilizations might indeed possess the technological capability to create simulated universes populated by conscious beings. This brings us to a curious recursive aspect of the simulation hypothesis. If we are simulated beings created by some advanced civilization, and if we eventually develop the ability to create our own simulations containing conscious entities, then those entities might also develop simulation technology. This could lead to an infinite regress of nested simulations, each level creating new virtual realities within their own virtual reality. The question then becomes not just whether we're in a simulation, but how many layers deep we might be in an endless stack of artificial realities. This question about the nature of reality isn't something that emerged alongside modern computers and digital technology. Humans have been wrestling with the possibility that their perceived reality might be fundamentally different from actual reality for thousands of years, long before anyone dreamed of silicon chips or virtual worlds. The simulation hypothesis, in many ways, is simply the latest chapter in an ancient philosophical conversation about illusion, truth, and the reliability of our senses. 2,400 years ago, in ancient Greece, the philosopher Plato crafted one of the most enduring metaphors about the nature of reality and human perception. His famous allegory of the cave, preserved in The Republic, tells the story of prisoners chained in an underground cavern from birth, their heads fixed so they can only look straight ahead at a blank wall. Behind them burns a fire, and between the fire and the prisoners, people carry objects that cast shadows on the wall. The prisoners, having never seen anything else, believe these flickering shadows are reality itself. In Plato's story, one prisoner eventually breaks free from his chains and turns around to see the fire and the objects casting the shadows. Initially, the bright light hurts his eyes and confuses him. The real objects seem less real than the shadows he's known all his life. But gradually he begins to understand that what he had taken for reality was merely a projection, a dim reflection of something more substantial and true. Eventually, this prisoner makes his way out of the cave entirely and discovers the sun, the ultimate source of light and truth, illuminating a world of genuine forms and objects. When this enlightened prisoner returns to tell his former companions about his discoveries, they refuse to believe him. The shadows on the wall seem more real to them than his descriptions of fire, objects, and sunlight. They're comfortable with their familiar illusions and hostile to truths that challenge their fundamental assumptions about the nature of existence. Plato used this allegory to explore the difference between the world of appearances, which we experience through our senses, and the world of forms, which we can only access through reason and philosophical contemplation. The parallels to our modern simulation hypothesis are striking and more than coincidental. Just as Plato's prisoners mistake shadows for reality, we might be mistaking computational processes for genuine physical existence. The cave represents our simulated environment, complete and convincing from the inside but ultimately artificial. The fire casting shadows could represent the computers running our simulation, creating the illusion of a physical world through carefully programmed processes. The prisoner who escapes and discovers the sun might represent someone who somehow breaks free from the simulation and discovers the true reality underlying their virtual existence. But Plato's allegory goes deeper than simple questions about illusion and reality. It's also about knowledge, education, and the difficulty of accepting truths that challenge our most basic assumptions. The freed prisoner's journey from ignorance to enlightenment mirrors the philosophical process of moving from accepting appearances to understanding deeper realities. His fellow prisoner's rejection of his discoveries reflects how difficult it can be to accept new paradigms that threaten our comfortable certainties. This philosophical tradition continued through the centuries, with thinkers regularly questioning whether our perceptions accurately reflect reality. Ancient skeptics like Pyrrho and Sextus Empiricus argued that we could never be certain about the true nature of things because all our knowledge comes through potentially unreliable senses. They pointed out that the same object can appear different to different observers, or even to the same observer under different conditions. A tower might look round from a distance, but square up close. Water might feel warm to a cold hand, but cool to a warm one. If our senses can be deceived about simple things like shape and temperature, how can we trust them about more fundamental questions? Medieval philosophers grappled with similar concerns, often in religious contexts. They wondered whether the physical world was substantial in its own right, or merely a reflection of divine reality. Some Islamic philosophers, particularly those influenced by Plato, suggested that the material world was like a shadow cast by a higher spiritual realm. Christian thinkers sometimes echoed these themes, seeing the physical world as a temporary illusion compared to eternal spiritual reality. During the Renaissance and early modern period, these ancient questions about reality and illusion took on new dimensions as scientific methods began to reveal that many common-sense beliefs about the world were wrong. The Earth wasn't the center of the universe as it appeared to be. Solid objects were mostly empty space, filled with tiny, invisible particles. Light sometimes behaved like waves, and sometimes like particles. The more scientists learned about the world, the more apparent it became that reality was quite different from everyday appearances. The simulation hypothesis can be seen as a natural extension of this long philosophical tradition, where ancient thinkers used metaphors of shadows and caves, dreams and illusions. We use the language of computation and information processing. But the underlying questions remain remarkably similar. How can we distinguish between appearance and reality? What if our most basic assumptions about existence are wrong? Is there a more fundamental reality underlying our everyday experiences? What makes the modern version particularly compelling, though, is that unlike purely philosophical speculation, the simulation hypothesis is potentially testable and certainly technologically plausible. Plato's prisoners could never really escape their cave because it existed only as a thought experiment. But if we're living in a computer simulation, that simulation runs on actual hardware operated by actual beings, which means there might be ways to detect signs of our artificial environment or even communicate with our programmers. The allegory of the cave also raises important questions about what we should do if we discover we're living in a simulation. Would knowledge of our simulated nature be liberating, like the freed prisoner's discovery of the sun, or would it be disturbing and destabilizing, making our relationships and experiences feel less meaningful? Plato suggested that the philosopher had a duty to return to the cave and try to enlighten others, even though they might reject or even attack him for challenging their comfortable illusions. Similarly, if we discovered evidence that we're simulated, would we have an obligation to share that knowledge even if it caused distress or disrupted society? These ancient philosophical questions have taken on new urgency in our digital age, but they remind us that humans have always lived with uncertainty about the ultimate nature of reality. Whether we're shadows on a cave wall or bits in a cosmic computer, the fundamental challenge remains the same. How do we live meaningful lives while acknowledging the limits of our knowledge and the possibility that our deepest assumptions might be wrong? In the 17th century, a French philosopher and mathematician named René Descartes set out to rebuild human knowledge from the ground up. He was troubled by the uncertainties and contradictions he saw in the learning of his time, and he wanted to find something, anything, that he could know with absolute certainty. His method was radical and thoroughgoing. He would doubt everything he possibly could, systematically questioning every belief, assumption, and piece of apparent knowledge until he found something that doubt could not touch. Descartes began his philosophical demolition project by questioning the reliability of his senses. After all, his eyes sometimes deceived him, showing him things that weren't there or failing to reveal things that were. Optical illusions, mirages, and dreams all demonstrated that sensory experience could be misleading. If his senses could deceive him about small things, why should he trust them about large ones? Perhaps the entire physical world as he experienced it was nothing more than an elaborate sensory illusion. But Descartes pushed his skeptical method even further. He imagined the possibility of what he called an evil demon, or evil genius, a supremely powerful and malicious being who might be systematically deceiving him about everything. This demon might be feeding him false sensations, implanting fake memories, and manipulating his thoughts to create the illusion of a world that didn't actually exist. Under the influence of such a being, Descartes might believe he had a body when he didn't, think he was sitting by a fire when no fire existed, or imagine he was writing when no paper or ink was real. This thought experiment pushed skepticism to its absolute limit. If an evil demon could deceive him about everything he thought he knew, including mathematics, logic, and even his own existence, was there anything at all that he could know with certainty? Descartes found that there was. Even if he was being systematically deceived about everything else, the very act of thinking, of being deceived, proved that he existed as a thinking being. He could doubt the existence of his body, the external world, other people, even mathematical truths, but he could not doubt that he was doubting. The famous conclusion followed, cogito ergo sum. I think, therefore I am. This single point of certainty became the foundation stone for Descartes' reconstruction of knowledge. From the undeniable fact of his own existence as a thinking being, he attempted to prove the existence of God, the reliability of clear and distinct perceptions, and ultimately the existence of the external world. Whether his reconstruction succeeded is a matter of ongoing philosophical debate, but his method of systematic doubt established a new standard for philosophical rigor and introduced questions about reality and deception that continue to resonate today. The parallels between Descartes' evil demon and our contemporary simulation hypothesis are impossible to ignore. Both scenarios involve a powerful external agent creating a false reality that is indistinguishable from the genuine article from the inside. The evil demon uses supernatural powers to implant false sensations and thoughts. The simulation programmers use advanced technology to create artificial experiences and perhaps artificial consciousness itself. In both cases, the deceived subject has no direct access to the true reality underlying their fabricated experiences. But there are important differences as well. Descartes' evil demon was conceived as a purely skeptical tool, a thought experiment designed to test the limits of doubt rather than a genuine hypothesis about the nature of reality. The demon was malicious, actively seeking to deceive and confuse. Our simulation hypothesis, by contrast, typically imagines programmers who might be running simulations for scientific research, entertainment, or other purposes that don't necessarily involve malicious deception. We might be simulated for the same reasons we study history or run computer models, to understand complex systems or explore alternative possibilities. Additionally, Descartes lived in a world where systematic deception required supernatural intervention. Only a being with godlike powers could manipulate reality so completely that a person would be unable to detect the manipulation. But we live in an age where sophisticated deception is increasingly possible through purely technological means. Virtual reality systems can fool our visual and auditory senses. Deepfake technology can create convincing videos of people saying and doing things they never actually did. Social media algorithms can create information bubbles so complete that people live in essentially different realities. Descartes' method of doubt also raises the question of what we should do if we cannot achieve certainty about the nature of our reality. He believed he could move from the certainty of his own existence to knowledge of the external world through rational argument. But what if that rational reconstruction fails? What if we're left with uncertainty about whether we're biological beings in a physical universe or digital entities in a computer simulation? Some philosophers argue that this uncertainty doesn't matter for practical purposes. If a simulation is indistinguishable from reality, then for all intents and purposes, it is reality. Your experiences remain your experiences. Your relationships retain their emotional significance, and your choices still have consequences within whatever framework of existence you inhabit. Whether the pain you feel when you stub your toe is caused by nerve signals or by programmed sensations doesn't change the fact that it hurts. Others find this response unsatisfying. They argue that questions about the ultimate nature of reality do matter, that there's an important difference between genuine and artificial experiences, even if that difference can't be detected from within the system. They might contend that discovering we're simulated would fundamentally change how we understand ourselves, our relationships, and our place in the cosmos. Descartes himself was confident that God's goodness would prevent the kind of systematic deception his evil demon represented. A perfect God would not allow humans to be fundamentally deceived about the nature of reality. But this theological solution is unavailable to those who don't share Descartes' religious assumptions. For them, the possibility of comprehensive deception, whether supernatural or technological, remains open. The Cartesian tradition of skepticism has profoundly influenced how we think about knowledge, reality, and consciousness. It established the principle that beliefs should be examined critically rather than accepted uncritically. It highlighted the central importance of consciousness in any account of human knowledge and existence. And it demonstrated that even our most basic assumptions about reality can and should be questioned. In our contemporary context, Descartes' method of systematic doubt provides a framework for thinking seriously about the simulation hypothesis. Just as he was willing to question everything except the bare fact of his own thinking existence, we might ask what we can know with certainty about our own reality. Can we be sure we have physical bodies? Can we be confident that other people exist independently of our perceptions of them? Can we trust that the laws of physics we observe reflect genuine features of reality rather than the programming constraints of our simulated environment? These questions might seem purely academic, but they have practical implications for how we understand consciousness, free will, moral responsibility, and the meaning of human existence. If Descartes taught us anything, it's that examining our most fundamental assumptions, even when that examination leads to unsettling conclusions, is essential for any serious attempt to understand our place in whatever reality we inhabit. In 1999, a film called The Matrix burst into popular culture and lodged itself permanently in the collective imagination. The story of Neo, a computer programmer who discovers that his entire reality is a simulated world created by machines, wasn't just science fiction entertainment. It was a philosophical treatise disguised as an action movie, exploring questions about knowledge, reality, and consciousness that philosophers had been wrestling with for centuries. The film's central conceit, that humans could be living in an elaborate simulation without knowing it, transformed abstract philosophical speculation into visceral, visual storytelling that millions of people could grasp immediately. The movie's most famous scene involves the character Morpheus offering Neo a choice between two pills. The red pill represents knowledge of the truth, no matter how disturbing that truth might be. The blue pill represents comfortable ignorance, a return to the familiar illusion of the Matrix, with no memory of having glimpsed reality. This choice crystallizes one of the most fundamental dilemmas human beings face. Do we want to know the truth about our existence, even if that truth is unpleasant, or would we prefer to live in comfortable delusion? The red pill or blue pill choice isn't just a plot device. It's a genuine philosophical question that extends far beyond science fiction. Throughout history, humans have been offered various versions of this same choice. Galileo could have kept quiet about his telescopic observations and avoided conflict with the Church. Darwin could have suppressed his theory of evolution to avoid challenging religious beliefs. Countless individuals have faced moments where they could choose between pursuing difficult truths or maintaining comforting illusions. In the context of the simulation hypothesis, this choice takes on particular urgency. If we discovered definitive evidence that we're living in a computer simulation, would we want to know? Would such knowledge improve our lives, or make them more meaningful? Or would it introduce existential anxiety and nihilistic despair that might be worse than ignorance? The Matrix suggests that most people would choose the blue pill, preferring familiar illusion to disturbing truth. The character Cypher, who betrays his fellow rebels to return to the Matrix, explicitly chooses ignorance over knowledge, trading the harsh reality of the real world for the pleasant simulation of being a wealthy, successful person in the artificial world. This raises profound questions about the relationship between truth and happiness, knowledge and well-being. If a simulation provides genuine pleasure, meaningful relationships, and fulfilling experiences, is there something inherently wrong with preferring it to a reality that might be harsh, disappointing, or meaningless? The film doesn't provide easy answers to these questions, but it forces viewers to confront them seriously. The Matrix also explores themes of determinism and free will that are central to the simulation hypothesis. If we're living in a programmed reality, are our choices genuinely free, or are we simply following predetermined scripts? The character of the Oracle represents a kind of middle ground, suggesting that the future is not entirely fixed, but that some aspects of it can be predicted with high confidence. Neo's journey involves learning to transcend the limitations of the simulated world, developing abilities that seem impossible within the rules of the Matrix. This aspect of the film touches on questions about the nature of consciousness and its relationship to physical reality. If consciousness can exist independently of biological processes, if it can manipulate digital environments through will and understanding, then perhaps the distinction between real and simulated becomes less important. The film suggests that consciousness itself might be the fundamental reality, with both the Matrix and the real world serving as different contexts in which consciousness operates. The movie's influence on how people think about simulation theory cannot be overstated. Before the Matrix, discussions of simulated reality were largely confined to academic philosophy and science fiction literature. After its release, these ideas entered mainstream discourse. The phrase "taking the red pill" became shorthand for accepting difficult truths, while blue pill thinking came to represent willful ignorance or denial of uncomfortable realities. However, The Matrix also simplified and dramatized these philosophical questions in ways that may have obscured their true complexity. The film presents a clear distinction between the false world of the Matrix and the real world outside it, but actual simulation theory suggests that the boundaries might be far less clear. If we're in a simulation, there might not be a simple outside to escape to, or the reality beyond our simulation might itself be simulated. The movie's action-adventure framework, while making these ideas accessible to general audiences, may have encouraged people to think about simulation theory in overly binary terms. The film's depiction of artificial intelligence as malevolent also shapes how many people think about the possibility that we might be simulated beings. In The Matrix, humans are essentially batteries being harvested for energy by machines that have conquered the world. But there's no particular reason to assume that if we're in a simulation, our programmers are hostile. They might be future humans studying their past, scientists exploring alternative histories, or beings with purposes we can't even imagine. The simulation might be designed for our benefit rather than our exploitation. Nevertheless, the Matrix succeeded in making abstract philosophical questions feel immediate and personally relevant. It demonstrated that questions about the nature of reality aren't just academic exercises, but potentially urgent, practical concerns. If there's even a small chance that we're living in a simulation, shouldn't we take that possibility seriously? The film's enduring popularity suggests that these questions resonate with something deep in human psychology, a persistent uncertainty about whether our perceptions accurately reflect reality. The movie also introduced the idea that recognizing the artificial nature of our reality might grant us special powers or freedoms. If the world is just code, then perhaps consciousness can learn to manipulate that code directly. This concept has influenced how some people think about meditation, lucid dreaming, and other practices that seem to alter the relationship between mind and perceived reality. While these ideas remain speculative, they point toward interesting questions about the relationship between consciousness and whatever substrate supports it. The Matrix remains culturally relevant more than 2 decades after its release because it tapped into fundamental questions about truth, reality, and human agency that each generation must grapple with anew. In our current era of deepfake technology, social media echo chambers, and increasingly convincing virtual reality systems, the film's themes feel more relevant than ever. We're all navigating a world where the line between authentic and artificial, between real and simulated, becomes increasingly blurred. In 2003, philosopher Nick Bostrom published a paper that would fundamentally change how scientists and philosophers think about the possibility that we might be living in a computer simulation. His argument, known as the simulation hypothesis or the simulation argument, wasn't just speculative fiction or abstract philosophical musing. It was a rigorous logical argument that suggested we should take seriously the possibility that our entire reality might be artificial. Bostrom didn't claim that we definitely are living in a simulation, but he demonstrated that unless certain specific conditions are met, we probably are. The elegance of Bostrom's argument lies in its structure. He presented what philosophers call a trilemma, a situation where exactly one of 3 propositions must be true, though we may not know which one. According to Bostrom's reasoning, at least one of the following statements must be correct. First, that technologically advanced civilizations almost always go extinct before developing the capability to run detailed simulations of their evolutionary history. Second, that advanced civilizations capable of running such simulations almost always lose interest in doing so. Or third, that we are almost certainly living in a computer simulation right now. Let's unpack each of these possibilities and their implications. The first proposition suggests that there might be some kind of great filter that prevents civilizations from reaching the technological sophistication necessary to create realistic simulations containing conscious beings. This could involve nuclear war, environmental collapse, pandemic diseases, or other catastrophic events that consistently destroy advanced societies before they can develop the computational power and understanding necessary for sophisticated reality simulation. If this proposition is true, it would explain why we don't seem to be living in a simulation. Nobody has ever developed the technology to create one. The second proposition allows that advanced civilizations might survive and develop incredible computational capabilities, but suggests that they consistently choose not to use these capabilities to run detailed historical simulations. Perhaps the ethical implications of creating billions of conscious beings who might suffer or die in simulated worlds are so troubling that advanced civilizations universally decide against such projects. Or perhaps they find other uses for their computational resources more interesting or valuable than recreating their past. Maybe they prefer to explore the future rather than revisit history, or they discover forms of entertainment and research that make ancestor simulations seem primitive or boring. The third proposition is the one that captures most people's attention and concern, that we are ourselves simulated beings, digital entities living in a computer program created by some advanced civilization. If this is true, then everything we think we know about physics, chemistry, biology, and the history of the universe might be programmed features of our artificial environment rather than discovered truths about fundamental reality. Bostrom's argument depends on several key assumptions about the nature of consciousness and computation. He assumes that consciousness can arise from purely computational processes, regardless of whether those processes occur in biological brains or silicon computers. This assumption, known as computational functionalism, suggests that what matters for consciousness is the pattern of information processing, not the physical substrate that implements that pattern. If this assumption is correct, then simulated beings could be genuinely conscious, capable of real experiences, thoughts, and emotions. He also assumes that advanced civilizations would have access to enormous computational resources and would be capable of running many detailed simulations simultaneously. If a single advanced civilization could run thousands or millions of detailed historical simulations, each containing billions of conscious beings, then the total number of simulated conscious beings would vastly exceed the number of non-simulated ones. From a purely statistical perspective, any randomly selected conscious being would be much more likely to be simulated than real. This statistical argument is both compelling and troubling. If you accept Bostrom's assumptions about consciousness and computation, and if you believe that advanced civilizations are likely to run ancestor simulations, then you should conclude that you are probably a simulated being. The math seems inescapable. If there are vastly more simulated people than real people, then you're probably one of the simulated ones. However, each of Bostrom's assumptions can be questioned. Computational functionalism, while popular among cognitive scientists and artificial intelligence researchers, remains unproven. We still don't fully understand how consciousness arises from brain activity, and it's possible that biological processes are necessary for genuine conscious experience. If consciousness requires something that only biological systems can provide, then computer simulations might create beings that behave as if they're conscious, without actually having inner experiences. The assumption about advanced civilizations running ancestor simulations also deserves scrutiny. Would future humans really want to simulate the entire history of their species, including all the suffering, conflict, and tragedy that history contains? Would they consider it ethical to create billions of conscious beings who would experience poverty, disease, war, and death? There might be strong moral arguments against running detailed historical simulations, especially if those simulations include genuine conscious suffering. Additionally, the computational requirements for simulating an entire universe down to the quantum level would be astronomical. Even with exponential advances in computing power, it might never become practical to create simulations detailed enough to be indistinguishable from reality at every level. However, Bostrom points out that you wouldn't necessarily need to simulate everything in perfect detail. Like a video game that only renders objects the player is currently observing, a universe simulation might use computational shortcuts, only modeling things when they're being observed or measured. The simulation argument has spawned extensive debate among philosophers, physicists, and computer scientists. Some argue that it proves too much, that if we take it seriously, we should also worry about even more exotic possibilities, like being Boltzmann brains. Random fluctuations in quantum fields that happen to have the organization of conscious minds complete with false memories of entire lifetimes. Others contend that the argument makes unfounded assumptions about the nature of consciousness or the motivations of advanced civilizations. Despite these criticisms, Bostrom's argument has been influential because it demonstrates that the simulation hypothesis isn't just science fiction speculation. If certain plausible assumptions about consciousness, computation, and the behavior of advanced civilizations are correct, then we should assign a significant probability to the possibility that we're living in a simulation. Whether that probability is 10%, 50%, or 99% depends on how confident we are in Bostrom's various assumptions, but his argument suggests we can't simply dismiss the simulation hypothesis as obviously false. The simulation argument also raises profound questions about the nature of reality, knowledge, and existence that extend far beyond its specific conclusions. If there's a reasonable chance we're simulated, how should that affect how we live our lives, treat other people, or think about our place in the cosmos? These questions don't have easy answers, but Bostrom's argument ensures that we can't avoid grappling with them seriously. Could computers actually simulate an entire universe? This isn't just a philosophical question anymore. It's become a practical engineering challenge that scientists and computer theorists are seriously attempting to quantify. The computational requirements for creating a convincing, simulated reality depend entirely on how detailed and comprehensive that simulation needs to be, and the answers might surprise you with both their enormity and their potential feasibility. Let's start with the most ambitious possibility: simulating every particle in the observable universe down to the quantum level. The observable universe contains approximately 80 atoms, each one potentially interacting with others according to the laws of quantum mechanics. If we wanted to track the quantum state of every particle and simulate every possible interaction, the computational requirements would be staggering. Some estimates suggest this would require around 120 operations per second, a number so large it's difficult to comprehend. To put this in perspective, the fastest supercomputers today can perform around 18 operations per second, meaning we'd need computers that are 102 times more powerful than anything currently available. That seems impossibly large, but let's consider the trajectory of computational progress. Moore's law, the observation that computing power roughly doubles every 2 years, has held remarkably steady for several decades. If this trend continues indefinitely, we would eventually reach the computational power necessary to simulate entire universes. Of course, Moore's law can't continue forever as we approach physical limits like the size of atoms, but even if the rate of progress slows, exponential improvement in computing capabilities could eventually make universe-scale simulations possible. However, there's a crucial insight that makes the computational challenge much more manageable. You probably don't need to simulate everything in perfect detail all the time. This principle is already familiar to anyone who's played video games or used computer graphics software. A video game doesn't need to model every atom in a virtual tree. It only needs to create the appearance of a tree detailed enough to convince the player. Similarly, a universe simulation might use what computer scientists call lazy evaluation, only computing details when someone is actually observing them. Consider how this might work in practice. If no conscious being is looking at a distant galaxy, the simulation might represent it with just a few basic parameters: position, mass, brightness. Only when someone points a telescope in that direction would the simulation need to generate detailed images of individual stars, planetary systems, and other features. This approach, sometimes called rendering on demand, could reduce the computational requirements by many orders of magnitude. The quantum nature of reality might actually make this computational shortcut more plausible. In quantum mechanics, particles don't have definite properties until they're measured. An electron doesn't have a specific position and momentum simultaneously. It exists in a superposition of possibilities until an observation collapses it into a definite state. This suggests that reality itself might work something like a lazy evaluation system, only computing specific details when they're needed for observation or interaction. This quantum mechanical insight has led some physicists to speculate that the fundamental nature of reality might already be computational. If the universe operates according to mathematical laws that can be expressed as algorithms, and if those algorithms only generate specific outcomes when measurements occur, then perhaps there's no meaningful distinction between a perfectly simulated universe and a real one. Both would be systems where mathematical relationships govern the behavior of information, and both would generate identical experiences for any conscious beings within them. The question then becomes whether we could create conscious beings within our simulations, and this brings us back to the fundamental mystery of consciousness itself. If consciousness arises from patterns of information processing, as many cognitive scientists believe, then sufficiently sophisticated computers should be able to support conscious experiences. The human brain, after all, is essentially a biological computer, processing information through networks of neurons that communicate via electrical and chemical signals. Current estimates suggest that the human brain performs roughly 10-16 operations per second and stores about 10-15 bits of information. These numbers are large, but not impossibly so. Today's most powerful computers already approach or exceed some of these capabilities, though they don't yet organize information in ways that create anything resembling human consciousness. However, if we understand consciousness as an emergent property of certain types of information processing, then creating conscious, simulated beings might be more a matter of software sophistication than raw computational power. The question of simulating consciousness becomes even more interesting when we consider that we wouldn't necessarily need to recreate human-type consciousness. Simulated beings might have forms of awareness and experience quite different from our own. They might process information faster or slower than biological minds, have different sensory capabilities, or experience time in ways we can't imagine. The diversity of possible conscious experiences in simulated worlds might far exceed anything that has evolved naturally. There's also the intriguing possibility of hierarchical simulations, where simulated beings themselves create simulations. If conscious entities in a simulated world develop their own computing technology, they might eventually create their own artificial realities populated with conscious beings. This could lead to nested layers of simulation, each one potentially less detailed than the level above it, but still providing rich experiences for its inhabitants. The computational requirements for such nested simulations might actually decrease at each level. Just as a video game character doesn't need to simulate the quantum mechanics of their virtual world to have meaningful experiences within it, each level of simulation could operate with simplified physics and reduced detail, while still supporting genuine consciousness and rich experiences. Modern developments in artificial intelligence and machine learning provide glimpses of how sophisticated simulation might work. Large language models can engage in complex conversations and demonstrate what appears to be understanding and creativity, even though they're essentially very sophisticated pattern-matching systems. Virtual reality environments are becoming increasingly convincing, and the boundary between real and synthetic media is rapidly blurring. These trends suggest that creating convincing simulated realities might not require the astronomical computational resources that full universe simulation would demand. Instead, we might need sophisticated algorithms that can generate believable experiences efficiently, combined with computational power that, while enormous by today's standards, might be achievable within decades or centuries rather than millennia. The implications are profound. If advanced civilizations can create detailed simulations containing conscious beings using computational resources that are large but not impossible to achieve, then Bostrom's simulation argument becomes much more compelling. The number of simulated conscious beings could vastly exceed the number of biological ones, making it statistically likely that any randomly selected conscious entity, including you, would be simulated rather than original. Quantum mechanics, the strange and counterintuitive theory that describes reality at its smallest scales, might offer some of the most intriguing clues about whether we're living in a simulation. The quantum world operates according to rules that seem almost tailor-made for computational efficiency, exhibiting properties that bear a striking resemblance to the kinds of shortcuts and optimizations that programmers use when creating virtual environments. While these parallels don't prove we're simulated, they're certainly curious enough to warrant careful consideration. Let's start with one of the most fundamental features of quantum mechanics, the uncertainty principle, discovered by Werner Heisenberg in the 1920s. This principle states that you cannot simultaneously measure certain pairs of properties, like a particle's position and momentum, with perfect precision. The more accurately you determine one property, the less accurately you can know the other. At first glance, this seems like a fundamental limitation of nature, but from a computational perspective, it looks remarkably like a processing constraint. Consider how video games handle similar challenges. A game cannot possibly store and display every detail of a virtual world simultaneously. It would require far too much memory and processing power. Instead, games use techniques like level of detail rendering, where objects far from the player are rendered with less precision than nearby objects. The uncertainty principle might serve a similar function in a simulated universe, preventing the system from having to compute and store precise values for properties that aren't being actively observed. The quantum measurement problem presents another computational parallel. In quantum mechanics, particles exist in superposition, simultaneously occupying multiple states until they're measured or observed. Only at the moment of measurement does a particle collapse into a definite state. This behavior is deeply puzzling from a classical physics perspective, but it makes perfect sense as a computational optimization strategy. Why waste processing power calculating the exact state of every particle in the universe when most of them aren't being observed by anyone? This resembles a technique in computer science called lazy evaluation, where calculations are only performed when their results are actually needed. A simulated universe might work the same way, maintaining particles in undefined superposition states until some interaction requires determining their specific properties. From this perspective, quantum measurement isn't a mysterious physical process. It's simply the universe's operating system running the necessary calculations when they're finally required. The quantization of energy levels in atoms provides another intriguing parallel. Electrons in atoms can only occupy specific energy levels, jumping between these discrete states rather than occupying intermediate positions. This quantum behavior has no classical analog, but it strongly resembles the way digital systems represent continuous values using discrete numbers. Just as digital computers represent smooth curves using pixels or represent analog signals using digital samples, the universe might represent continuous physical properties using discrete quantum units. The speed of light presents yet another computational hint. In our universe, nothing can travel faster than light, and information cannot be transmitted instantaneously across space. This creates a fundamental limit on how quickly changes can propagate through the universe. From a computational standpoint, this looks very much like a processing constraint. A simulated universe would need some maximum rate at which information can be updated and shared between different parts of the simulation, and the speed of light might represent exactly this kind of computational bottleneck. Similarly, the Planck length and Planck time represent the smallest meaningful distances and time intervals in physics. Below these scales, the very concepts of space and time begin to break down. This resembles the pixel resolution of a digital display or the frame rate of a video game. Just as digital systems have fundamental limits on their precision and resolution, our universe appears to have built-in minimum units for space and time. Even the apparent randomness of quantum mechanics could be seen as a computational feature. True randomness is actually quite difficult to generate using deterministic computers, but quantum mechanics seems to provide genuine randomness in processes like radioactive decay and particle interactions. However, from a simulation perspective, this randomness might not need to be truly random. It would just need to be unpredictable enough that simulated beings couldn't detect the underlying pattern or algorithm. The many worlds interpretation of quantum mechanics adds another layer to these computational analogies. According to this interpretation, every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different possible outcome. While this sounds wildly extravagant, it might actually be computationally efficient. Rather than having to determine which specific outcome occurs in each quantum event, the simulation could simply branch into multiple versions, exploring all possibilities simultaneously. However, we must be careful not to read too much into these parallels. The fact that quantum mechanics has features that would be useful in a computer simulation doesn't necessarily mean we're living in one. These quantum properties might simply be fundamental features of reality that have nothing to do with computation. The uncertainty principle might reflect genuine limitations on what can be known about physical systems, rather than processing constraints. Quantum superposition might be a real physical phenomenon rather than a computational shortcut. Additionally, many features of quantum mechanics would actually make simulation more difficult, not easier. The quantum entanglement phenomenon, where particles become correlated in ways that persist across arbitrary distances, would require the simulation to maintain complex relationships between particles that might be separated by vast regions of space. The exponential growth in complexity that occurs when quantum systems interact would make simulating large quantum systems extremely challenging. There's also the question of whether our current understanding of quantum mechanics is complete and accurate. The theory has been remarkably successful in making predictions and explaining observations, but physicists continue to debate its interpretation and search for more fundamental theories. If our understanding of quantum mechanics changes significantly, the computational parallels we currently observe might disappear or be revealed as coincidental. Some physicists have proposed experiments that might detect signs of computational constraints in our universe. These might involve looking for pixelation effects at the smallest scales, searching for computational shortcuts in the way physical laws operate, or trying to identify glitches or inconsistencies that might reveal the underlying simulation. However, a sophisticated simulation might be designed to pass any test we could conceive, making such experiments extremely challenging. The relationship between quantum mechanics and consciousness adds yet another layer of complexity to these questions. Some interpretations of quantum mechanics suggest that conscious observation plays a special role in collapsing quantum superpositions. If this is true, and if consciousness itself is a computational process, then the boundary between quantum physics and simulation theory becomes even more blurred. Whether or not quantum mechanics provides evidence for the simulation hypothesis, it certainly demonstrates that reality at its most fundamental level operates according to principles that seem strange and non-intuitive from our everyday perspective. The quantum world is already so removed from classical reality that discovering we're living in a simulation might not be much more surprising than discovering that particles can be in multiple places at once, or that measuring one particle can instantaneously affect another particle on the opposite side of the galaxy. If we're living in a computer simulation, we might expect to find glitches, processing limits, or computational shortcuts that reveal the artificial nature of our reality. After all, no program is perfect, and even the most sophisticated simulation might have bugs, optimization strategies, or resource constraints that occasionally become visible to careful observers. Some researchers have proposed looking for these digital fingerprints in the fabric of reality itself, searching for evidence that our universe operates more like a computer program than a continuous physical system. The search for glitches in reality has led some to examine unexplained phenomena in physics as potential bugs in our cosmic software. Dark matter, the mysterious substance that seems to make up about 85% of all matter in the universe, could theoretically be a placeholder or simplified representation used by the simulation to account for gravitational effects without having to render detailed matter that nobody would observe directly. From a programming perspective, it would make sense to use computational shortcuts for matter that affects gravity but doesn't interact with light or ordinary matter in observable ways. Similarly, dark energy, the even more mysterious force that appears to be accelerating the expansion of the universe, might represent another kind of computational approximation. Rather than simulating the complex interactions that would naturally lead to cosmic expansion, the simulation might simply apply a universal expansion algorithm that produces the same observable effects with far less computational overhead. These explanations are highly speculative, but they demonstrate how apparently mysterious aspects of our universe might have computational rather than purely physical origins. Quantum uncertainty, which we discussed earlier as a potential computational optimization, could also be viewed as evidence of processing limits in our simulated reality. The fact that nature seems to have built-in limits on precision and measurement might reflect the finite computational resources available to whatever system is running our simulation. Just as digital photographs have pixel resolution limits and computer animations have frame rate constraints, our universe might have fundamental limits that reflect the computational architecture underlying it. Some scientists have proposed looking for evidence of discrete space-time structure at the smallest scales, something like pixels in the fabric of reality itself. If space and time are continuous, as classical physics suggests, then you should be able to divide them into arbitrarily small units. But if reality is fundamentally digital, there should be minimum units beyond which further division becomes impossible or meaningless. The Planck length and Planck time, which represent the smallest meaningful scales in current physics, might be evidence of such digital structure, though they could also simply reflect fundamental features of continuous space-time. Another area where glitches might appear is in the consistency of physical laws across different scales or contexts. In computer simulations, different parts of the virtual world often use different algorithms optimized for specific purposes. A space simulation might use one algorithm for planetary motion, another for stellar evolution, and a third for quantum mechanics. If our universe is simulated, we might expect to find subtle inconsistencies where these different algorithmic domains interface with each other. The famous double-slit experiment in quantum mechanics, where particles behave differently depending on whether they're being observed, might represent exactly this kind of algorithmic switching. When nobody is measuring which slit a particle goes through, the simulation might use a wave-based algorithm that's computationally efficient for modeling probability distributions. But when a measurement is made, the system switches to a particle-based algorithm that provides definite outcomes. The transition between these two computational modes could explain the seemingly paradoxical wave-particle duality of quantum mechanics. However, searching for glitches in reality faces fundamental challenges. The most obvious problem is that any glitch we could detect might simply be patched by the simulation's operators once they notice we've found it. If advanced beings are running our simulation, they presumably have the ability to modify it in real time, correcting errors and updating algorithms as needed. A truly sophisticated simulation might even be self-correcting, automatically fixing inconsistencies before they become noticeable to simulated beings. More problematically, our entire understanding of what constitutes normal versus glitchy behavior comes from within the simulation itself. We determine what counts as a physical law or natural phenomenon based on observations made from inside our reality. If we discovered that gravity occasionally behaves strangely in certain circumstances, how would we distinguish between a glitch in our simulation and a previously unknown natural phenomenon? Our expectations about how reality should behave are themselves products of living within whatever system we're trying to evaluate. There's also the question of whether apparent glitches might actually be features rather than bugs. Many of the strange aspects of quantum mechanics that we might interpret as computational shortcuts could be fundamental features of reality that have nothing to do with simulation. The uncertainty principle, quantum entanglement, and wave function collapse might reflect genuine properties of the universe rather than programming constraints or optimizations. Additionally, the absence of obvious glitches doesn't necessarily mean we're not simulated. It might simply mean that the simulation is extremely well designed and thoroughly tested. Advanced civilizations running ancestor simulations would presumably want to avoid obvious anachronisms or inconsistencies that might tip off their simulated subjects. They might run extensive quality assurance processes to ensure their simulated realities are indistinguishable from genuine ones. The computational limits argument faces similar challenges. While our universe does seem to have various speed limits, precision limits, and minimum units, these might be necessary features of any possible reality rather than artificial constraints imposed by simulation. Even a non-simulated universe might need maximum information transfer rates, minimum meaningful distances, and finite computational resources at the quantum level. Some physicists have proposed more sophisticated experiments to detect simulation artifacts, such as looking for correlations in apparently random quantum events that might reveal underlying algorithmic patterns, or searching for statistical anomalies in cosmic background radiation that might indicate computational compression or approximation techniques. However, these experiments face the fundamental challenge that a sufficiently advanced simulation could be designed to pass any test we might devise. Perhaps the most we can hope for is indirect evidence, rather than definitive proof. If we discovered that certain physical phenomena become much easier to understand when viewed as computational processes, rather than continuous physical interactions, That might provide circumstantial support for the simulation hypothesis. Similarly, if we found that the most fundamental laws of physics could be expressed more naturally as algorithms than as differential equations, that might suggest an underlying computational reality. The search for glitches in reality represents humanity's attempt to peek behind the curtain of existence, to determine whether the stage on which we perform our lives is genuine or artificial. Whether or not we ever find definitive evidence, the search itself reveals something important about human nature: our persistent desire to understand the true nature of our reality, even when that truth might be stranger and more unsettling than we ever imagined. The simulation hypothesis raises a puzzling question that strikes at the heart of causality and identity. If we are simulated beings created by some advanced civilization, who exactly is running our simulation, and why? This question opens up a labyrinth of recursive possibilities and paradoxes that challenge our understanding of time, purpose, and the relationship between creators and their creations. The most commonly proposed answer is both elegant and deeply strange. We might be simulated by our own descendants, future humans who have developed the computational power to recreate their evolutionary history in digital form. This scenario, often called ancestor simulation, suggests that future humans might run detailed simulations of their past for scientific, historical, or cultural reasons. Just as we study ancient civilizations through archaeology and historical research, our technologically advanced descendants might study their origins by simulating the entire sweep of human history from prehistoric times through the present moment. In this view, you and everyone you know would be digital recreations of people who once lived in the original timeline, your lives playing out again in silicon and software for the education or entertainment of beings you might not even recognize as human. The ancestor simulation hypothesis creates immediate temporal paradoxes that are difficult to resolve. If we are simulations created by our descendants, then our simulated actions and decisions presumably influence the course of history that leads to those same descendants. But this creates a circular causality problem. Our descendants exist because of historical events that include our lives, but our lives are being simulated by those very descendants. Which came first, the original history or the simulation of it? Did the events we're experiencing happen first in some baseline reality, or are we living through the primary occurrence of these events in simulated form? The paradox deepens when we consider that our simulated actions might need to match the historical record that our descendants are trying to recreate. If they're simulating us to understand how specific historical events unfolded, then presumably our simulated behavior needs to align with whatever actually happened in the original timeline. This suggests we might not have genuine free will, but are instead following predetermined scripts based on historical records. Yet this interpretation faces the problem that many of our choices and experiences are too private and personal to appear in any historical record that our descendants might possess. Alternatively, our descendants might be running exploratory simulations rather than strict historical recreations. Instead of trying to reproduce exactly what happened in the past, they might be investigating alternative histories or exploring how different initial conditions might have led to different outcomes. In this scenario, we could have genuine agency and free will within our simulated environment, even though our entire reality is artificial. Our choices would be real choices with real consequences, just occurring within a digital rather than biological context. The motivations for running ancestor simulations could be varied and complex. Scientific curiosity seems like an obvious driver. Future humans might want to understand the conditions that led to their own emergence, the factors that shaped their culture and technology, or the decision points that determined their civilization's trajectory. By running detailed simulations of their past, they could gain insights into alternative possibilities and better understand the historical forces that shaped their world. Cultural and emotional motivations might also play a role. Perhaps our descendants run simulations to maintain connection with their origins, to experience directly the lives of their ancestors, or to preserve the memory of earlier eras in vivid detail. These simulations might serve functions similar to those served by museums, historical fiction, or genealogical research in our current culture, but with the added dimension of creating actual conscious experiences rather than mere representations. Educational purposes provide another possible motivation. Rather than learning about history through books and documentaries, future students might experience historical periods directly through simulation. Imagine learning about the 21st century by actually living through a simulated version of it, experiencing firsthand the challenges, conflicts, and transformations of our era. Such immersive historical education would provide unprecedented insight into the past, though it would raise profound ethical questions about creating conscious beings for educational purposes. The ethics of ancestor simulation present troubling dilemmas that our descendants would need to grapple with. If simulated beings are genuinely conscious and capable of suffering, then running historical simulations that include war, disease, poverty, and death would involve creating enormous amounts of genuine suffering for research or entertainment purposes. Would it be morally acceptable to recreate the Black Death, World War II, or the COVID-19 pandemic if doing so caused real pain and death for billions of conscious beings, even if those beings exist only in digital form? These ethical concerns might explain why advanced civilizations choose not to run detailed ancestor simulations, supporting the second proposition in Bostrom's trilemma. Perhaps the moral implications of creating conscious beings who will suffer and die in simulated historical events are so troubling that advanced civilizations consistently decide against such projects, preferring other uses for their computational resources. The observer problem in ancestor simulation creates additional complications. If our descendants are studying us through simulation, how do they observe what happens without interfering with the natural course of events? Any direct intervention or obvious monitoring would presumably alter the behavior of simulated beings who noticed they were being watched. This might require sophisticated techniques for observing simulated realities without affecting them, or it might limit the kinds of information that can be gathered from such simulations. There's also the question of multiple simulation layers. If our descendants create simulations of their past, and if we within those simulations eventually develop our own simulation technology, we might create our own ancestor simulations. This could lead to an infinite regress of nested simulations, with each level creating simulations of their own past, creating a vast hierarchy of digital realities stacked on top of each other like an endless series of mirrors reflecting into eternity. The computational requirements for detailed ancestor simulation would be enormous, but perhaps not impossible for sufficiently advanced civilizations. Simulating every human brain for thousands of years of history would require processing power far beyond anything currently available, but if computational capabilities continue to grow exponentially, such simulations might eventually become feasible. The question then becomes whether advanced civilizations would choose to use their computational resources for ancestor simulation or for other purposes we can't currently imagine. Perhaps the most unsettling aspect of the ancestor simulation hypothesis is its implications for our sense of purpose and authenticity. If we are digital recreations of people who once lived real lives in a real world, what does that mean for our relationships, achievements, and experiences? Are we genuine individuals with our own inherent worth, or are we merely copies, echoes of people whose real lives have already concluded? These questions challenge fundamental assumptions about identity, consciousness, and the meaning of existence in ways that few other philosophical problems can match. The hardest question raised by the simulation hypothesis involves consciousness itself, that mysterious inner experience of being aware, of feeling, of having subjective thoughts and emotions. We still don't fully understand how biological brains create the rich inner world of human experience, that continuous stream of sensations, memories, and thoughts that constitutes your mental life. The problem becomes even more complex when we ask whether digital computers could support genuine consciousness, or whether simulated beings would actually experience anything at all. Consider what it means for you to be conscious right now. You're not just processing information about these words, you're experiencing the act of understanding them. You have subjective feelings about the ideas being presented, perhaps curiosity, skepticism, or drowsiness. There's something it's like to be you, listening to this exploration of simulation theory, and that subjective experience seems fundamentally different from mere information processing. The question is whether this inner experience could arise from purely computational processes running on silicon and software. The dominant view in cognitive science, known as computational functionalism, suggests that consciousness emerges from patterns of information processing rather than from specific biological substrates. According to this perspective, what matters for consciousness is not the particular material that implements mental processes, but the abstract computational relationships between different information processing components. If this view is correct, then consciousness is substrate independent, meaning it could arise in digital computers just as naturally as it arises in biological brains. This functionalist approach treats the brain like biological hardware running the software of mind. Just as the same computer program can run on different types of processors and produce identical results, consciousness might be a kind of software that could run on biological neurons, silicon chips, or potentially any sufficiently complex information processing system. If consciousness is indeed substrate independent, then simulated beings could have genuine inner experiences, real emotions, and authentic subjective awareness. However, this computational view of consciousness faces significant challenges and critics. Some philosophers and scientists argue that consciousness requires something more than mere information processing, something that only biological systems can provide. They point to the specific chemical and electrical properties of neurons, the role of quantum effects in microtubules, or other biological processes that might be necessary for genuine awareness. According to these perspectives, digital simulations might create beings that behave exactly like conscious entities without actually having any inner experience. This leads to the philosophical zombie problem, a thought experiment that highlights the difficulty of determining whether apparent consciousness is genuine. A philosophical zombie would be physically or computationally identical to a conscious being but would lack any subjective inner experience. Such a zombie would behave exactly like a conscious person, claiming to have thoughts and feelings, responding appropriately to questions about their mental states, and exhibiting all the external signs of awareness, but there would be nothing it's actually like to be that entity. The zombie problem creates a troubling possibility for the simulation hypothesis. If we're living in a computer simulation, we might all be zombies, going through the motions of consciousness without actually experiencing anything. From the outside, our behavior would be indistinguishable from that of genuinely conscious beings, but there would be no inner experience accompanying our actions. This possibility is particularly unsettling because it's inherently undetectable. There would be no way to determine from within the system whether we're genuine conscious beings or merely sophisticated automatons. Alternatively, consciousness might exist on a spectrum rather than being a binary property. Perhaps simulated beings could have forms of awareness that are different from but not necessarily inferior to biological consciousness. Digital minds might process information faster or slower than biological brains, have different types of sensory experiences, or organize memories and emotions in ways that biological creatures cannot. The diversity of possible conscious experiences in simulated worlds might far exceed anything that has evolved naturally. The question of machine consciousness has practical implications beyond theoretical philosophy. As artificial intelligence systems become increasingly sophisticated, we're already beginning to grapple with questions about whether they might have genuine experiences or merely simulate the appearance of understanding and awareness. Large language models can engage in conversations that seem to demonstrate insight, creativity, and even emotional responses, but determining whether these responses reflect genuine inner experiences remains extremely difficult. Some researchers have proposed tests for machine consciousness, similar to the famous Turing test for intelligence, but these face the fundamental problem that consciousness is inherently subjective and private. You can observe the external behavior of another being, but you cannot directly access their inner experience. This creates what philosophers call the problem of other minds. Even with other humans, we must infer consciousness from behavior rather than observe it directly. The simulation hypothesis adds another layer of complexity to these consciousness puzzles. If we discovered that we're living in a simulation, would that change how we understand our own consciousness? Would knowing that our awareness arises from digital processes rather than biological ones make our experiences feel less real or meaningful? These questions touch on fundamental assumptions about the relationship between mind and matter, consciousness and computation. Some philosophers argue that the source of consciousness doesn't affect its reality or value. Whether your thoughts and emotions arise from neurons firing in a biological brain or from transistors switching in a digital computer, the subjective experience itself remains equally real and significant. Pain still hurts, joy still feels wonderful, and love still creates profound meaning, regardless of the underlying substrate that generates these experiences. Others find this view unsatisfying, arguing that there's something special about biological consciousness that cannot be replicated artificially. They might contend that digital simulations, no matter how sophisticated, would always be imitations rather than genuine instances of consciousness. From this perspective, discovering we're simulated would fundamentally change how we understand the nature and value of our experiences. The consciousness question in simulation theory also intersects with debates about personal identity and continuity of experience. If you were uploaded into a computer simulation, would the resulting digital being be you, or merely a copy that thinks it's you? Would there be continuity between your biological consciousness and your digital consciousness, or would the upload process create a new being with your memories but a fundamentally different identity? These questions about consciousness in simulated realities don't have easy answers, and they may ultimately be unanswerable given our current understanding of awareness and subjective experience. However, they force us to examine our assumptions about the nature of mind, the relationship between consciousness and physical processes, and the criteria we use to determine what counts as genuine versus artificial experience. Whether consciousness can exist in simulated worlds remains one of the deepest and most challenging questions raised by the simulation hypothesis. The answer shapes not only our understanding of simulated realities, but also our fundamental conception of what it means to be aware, conscious beings in whatever kind of universe we actually inhabit. If simulations can contain conscious beings, and if those conscious beings eventually develop their own technology and computational capabilities, they might eventually create simulations of their own. This possibility leads to one of the most mind-bending implications of the simulation hypothesis: the potential for infinite nested realities, simulations within simulations, stretching down through layers of artificial worlds like an endless series of Russian dolls. Each level might contain beings who believe their reality is fundamental, unaware of the deeper layers of simulation stacked both above and below them. Consider how this recursive process might unfold. Imagine that we are indeed living in a simulation created by some advanced civilization. As our simulated technology progresses, we might eventually develop computers powerful enough to run detailed simulations of our own history or alternative realities. The beings we create in our simulations would be just as real and conscious as we are, existing at what we might call the second level of simulation. But there's no reason the process would stop there. Those second-level beings might themselves develop simulation technology and create their own artificial worlds, populated by third-level simulated beings. This process could continue indefinitely, creating a vast hierarchy of nested realities. Each level would be slightly less detailed than the level above it, as computational resources would need to be divided among multiple simulations, but each level could still provide rich, meaningful experiences for its inhabitants. The beings at each level would experience their reality as complete and fundamental, unaware that they exist within a simulated world that is itself embedded within another simulated world. The mathematics of nested simulations are staggering to contemplate. If each level of simulation creates multiple sub-simulations, the total number of conscious beings could grow exponentially with each new layer. A single top-level civilization might ultimately be responsible for billions or trillions of nested worlds, each containing countless conscious entities living full, meaningful lives in their respective layers of reality. The vast majority of conscious beings in such a system would exist in the deeper simulation layers, far removed from whatever baseline reality anchors the entire hierarchy. This scenario raises profound questions about the nature of reality itself. In a world of infinite nested simulations, what would it mean for something to be real rather than artificial? Each level of simulation would be equally valid from the perspective of its inhabitants. A being living in the 10th level of simulation would have experiences just as genuine and meaningful as someone in the first level or the baseline reality. Their relationships, achievements, and emotions would be every bit as significant to them, regardless of how many layers of computation separate them from some original physical universe. The concept of nested realities also challenges traditional notions of causality and dependency. While it might seem that higher levels of simulation are more fundamental because they create and sustain the lower levels, this relationship might not be as clear-cut as it initially appears. The beings in lower-level simulations might make discoveries or develop technologies that influence the programming of their parent simulation. Information and innovations might flow both up and down the hierarchy of nested worlds. Some science fiction authors have explored the possibility that inhabitants of lower-level simulations might become aware of their simulated nature and attempt to communicate with or influence their programmers. They might try to send messages upward through the simulation hierarchy, or even attempt to escape their level of reality by somehow transferring their consciousness to a higher level. Whether such communication or escape would be possible would depend on how the simulations are designed, and whether the programmers at each level choose to allow such interactions. The nested simulation scenario also creates interesting paradoxes about computational resources and sustainability. Each level of simulation requires computational power from the level above it, and that computational demand multiplies as you add more levels and more simulations at each level. At some point, the computational requirements might become so large that the system becomes unsustainable, leading to crashes, slowdowns, or forced termination of some simulation branches. However, there might be ways to manage these computational demands efficiently. Lower levels might operate with simplified physics, reduced detail, or compressed timescales. Just as video games use various optimization techniques to create believable worlds without simulating every atom, nested simulations might use increasingly aggressive shortcuts as you move deeper into the hierarchy. The inhabitants of these simplified worlds wouldn't necessarily notice the reduced complexity if it's implemented skillfully. The nested simulation hypothesis also raises questions about the ultimate origin of the entire system. If every level of reality is simulated, what grounds the whole hierarchy? There must be some baseline level that provides the computational substrate for all the nested simulations, but that baseline might itself be quite different from any of the simulated worlds it supports. The beings inhabiting the fundamental reality might be so alien or advanced that the simulated worlds they create bear little resemblance to their own existence. Alternatively, the hierarchy might be circular rather than linear. Perhaps the baseline reality is itself a simulation created by beings who exist in one of the supposedly lower levels of the system. This would create a closed loop of interdependent realities, each one sustaining and being sustained by others in the loop. While such a system seems logically paradoxical, it might be possible in a universe where time, causality, and computational dependencies work differently than we currently understand. The philosophical implications of nested simulations extend to questions about moral responsibility and ethical obligations. If the beings in your simulation are genuinely conscious, do you have responsibilities toward them similar to those you have toward other conscious beings in your own reality? Should the welfare of simulated beings factor into moral calculations? If you have the power to create or terminate simulated worlds, what ethical constraints should guide those decisions? These questions become even more complex when multiplied across multiple levels of nested reality. The creators of your reality might face similar ethical dilemmas about their obligations to you, while you might face those same dilemmas about any simulated beings you create. The total moral weight of decisions made at higher levels of the hierarchy could be enormous, affecting not just the direct inhabitants of a simulation, but all the nested levels of conscious beings that might emerge from it. From a practical perspective, the nested simulation hypothesis suggests that the question of whether we're simulated might be less important than we initially think. If reality consists of vast hierarchies of nested simulations, then almost everyone is simulated to some degree. The distinction between real and artificial becomes a matter of relative perspective rather than an absolute binary. What matters might not be whether you're simulated, but whether you're living a meaningful life within whatever level of reality you happen to inhabit. The possibility of nested simulations represents one of the most elaborate and mind-expanding implications of taking the simulation hypothesis seriously. It suggests that reality might be far stranger and more layered than we ever imagined, consisting not of a single universe, but of countless interwoven worlds, each as real and significant as any other from the perspective of its inhabitants. Can we design experiments to test whether we're living in a computer simulation? This question moves us from philosophical speculation into the realm of empirical science, where hypotheses must be tested against observable evidence. Several physicists and computer scientists have proposed ingenious ways to search for signs that our reality might be computational, though each approach faces significant challenges and limitations that make definitive proof extremely difficult to achieve. One of the most direct approaches involves looking for evidence of computational shortcuts or optimizations that might be built into a simulated universe. Just as video games use techniques like level of detail rendering to save computational resources, a simulated reality might employ similar strategies to reduce processing demands. For instance, distant objects might be rendered in less detail than nearby ones, or physical processes might be approximated rather than calculated exactly when no one is observing them closely. Some researchers have proposed searching for pixelation effects at the smallest scales of space and time. If reality is fundamentally digital rather than continuous, there should be minimum units below which further division becomes impossible. While current physics already suggests the existence of such units in the form of Planck length and Planck time, detecting whether these represent genuine physical limits or computational constraints would require experiments at energy scales far beyond our current technological capabilities. Another experimental approach involves looking for statistical patterns in apparently random events that might reveal underlying algorithmic generation. True randomness is actually quite difficult for computers to produce. Most systems use pseudorandom number generators that create sequences of numbers that appear random but are actually generated by deterministic algorithms. If quantum mechanical events like radioactive decay or particle interactions show subtle statistical biases or correlations that suggest algorithmic generation rather than genuine randomness, this might provide evidence for simulation. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates the entire universe, presents another potential testing ground. This radiation contains tiny fluctuations that form the seeds of all large-scale structure in the universe. If our universe is simulated, these fluctuations might show signs of compression artifacts or algorithmic generation patterns similar to those found in computer-generated images or sounds. However, detecting such patterns would require incredibly sophisticated analysis and might be impossible if the simulation uses sufficiently advanced algorithms. Some proposals focus on detecting computational limits or resource constraints that might become apparent during high-energy or high-complexity events. If our reality runs on finite computational resources, there might be situations where the system struggles to keep up with processing demands, leading to glitches, slowdowns, or simplified calculations. Particle accelerator experiments that create extremely complex quantum states might reveal signs of such limitations, though distinguishing computational constraints from genuine physical limits would be challenging. The quantum measurement problem offers another avenue for investigation. The fact that quantum systems seem to exist in superposition until measured might reflect computational optimization, with the system only calculating definite states when they're actually needed. Experiments designed to force the simulation to perform large numbers of simultaneous quantum calculations might reveal signs of processing constraints or unusual behaviors that suggest computational rather than physical origins. However, all of these experimental approaches face a fundamental challenge known as the problem of indistinguishability. A sufficiently sophisticated simulation would presumably be designed to pass any test that its inhabitants could conceive. The programmers running our simulation would presumably want to avoid obvious glitches or inconsistencies that might tip off their simulated subjects. They might monitor our scientific progress and patch any vulnerabilities we discover, or they might simply design the simulation to be robust enough that no feasible experiment could distinguish it from genuine reality. This leads to an even deeper problem. Our understanding of what constitutes normal versus anomalous behavior comes entirely from within our own reality. If we discovered that gravity behaves strangely under certain exotic conditions, how would we know whether this represents a bug in our simulation or simply a previously unknown aspect of genuine physics? Our expectations about how reality should behave are themselves products of living within whatever system we're trying to evaluate. The self-correcting possibility presents another challenge to experimental detection. A sophisticated simulation might be designed to automatically fix inconsistencies or errors before they become apparent to observers. Any glitch we might detect could be corrected in real time, with our memories of the anomaly potentially altered to maintain consistency. This possibility makes the simulation hypothesis potentially unfalsifiable, placing it closer to philosophy than empirical science. Some physicists have proposed more subtle approaches based on information theory and computational complexity. They suggest looking for evidence that physical laws are organized in ways that suggest computational efficiency rather than fundamental necessity. If the universe operates according to algorithms that seem optimized for computational implementation rather than mathematical elegance, this might provide circumstantial evidence for simulation. The holographic principle in physics, which suggests that all the information in a volume of space can be encoded on its boundary, bears some resemblance to compression techniques used in computer graphics and simulation. Some researchers wonder whether this principle reflects computational optimization in a simulated universe, though it might also represent a genuine feature of quantum gravity that has nothing to do with artificial simulation. There's also the possibility of detecting communication channels or data structures that might exist outside our normal physical experience. If our simulation is being monitored or controlled by external operators, there might be hidden information channels or control mechanisms that could be detected through careful observation or experimentation. However, such channels would presumably be well hidden and protected against discovery by simulated beings. Perhaps the most promising approach involves looking for correlations or patterns across large scales that might be difficult to fake convincingly. The distribution of galaxies, the properties of cosmic microwave background radiation, or the behavior of quantum systems across vast regions of space might contain signatures that are difficult to simulate accurately. However, advanced civilizations with sufficient computational power might be able to create arbitrarily convincing large-scale patterns. The experimental search for simulation evidence also raises important questions about what we should do if we actually find it. Would discovering that we're simulated change how we live our lives or treat other people? Would it create existential crises or social upheaval? Some argue that the search for simulation evidence should proceed carefully, with consideration for the potential psychological and social consequences of positive results. Ultimately, the experimental investigation of the simulation hypothesis represents humanity's attempt to peek behind the curtain of reality itself. Whether or not we ever find definitive evidence, the search forces us to think carefully about the nature of reality, the limits of empirical knowledge, and the relationship between computation and consciousness. Even negative results would be scientifically valuable, helping us understand the constraints and possibilities of our universe, whatever its ultimate nature might be. Perhaps the most intellectually honest response to the simulation hypothesis is also the most frustrating. We may never know for certain whether we're living in a simulated reality or a genuine physical universe. This uncertainty isn't necessarily a failure of science or philosophy. It might simply reflect fundamental limits on what can be known from within any given system of reality. The possibility that we can never definitively resolve the simulation question forces us to confront how we should live and think when faced with profound uncertainty about the nature of our existence. This epistemic humility, the acknowledgement that some questions may be permanently beyond our ability to answer, has deep roots in philosophical tradition. Ancient skeptics argued that we can never achieve absolute certainty about the external world, because all our knowledge comes through potentially unreliable senses and reasoning processes. Modern philosophy has grappled with similar themes, recognizing that our perspective on reality is always limited by our position within that reality and our cognitive constraints as finite beings. If the simulation hypothesis cannot be definitively resolved, then perhaps the question of whether we're simulated becomes less important than how we respond to that uncertainty. Some philosophers argue that a perfectly convincing simulation would be functionally equivalent to reality for all practical purposes. If you cannot detect any difference between a simulated and genuine experience, and if that experience includes genuine consciousness, authentic relationships, and meaningful emotions, then the distinction might be philosophically interesting, but practically irrelevant. Consider your daily experience of existence. You wake up, interact with other people, pursue goals and projects, experience joy and sorrow, form memories and relationships. Whether these experiences arise from biological processes in a physical universe or from computational processes in a simulated one, they remain your experiences. The love you feel for family and friends doesn't become less real if it emerges from algorithms rather than neurochemistry. The beauty of a sunset doesn't lose its power to move you if the photons hitting your retinas are simulated rather than genuine. This pragmatic approach to the simulation question echoes themes in American pragmatist philosophy, which suggests that the meaning and value of ideas should be judged by their practical consequences rather than their correspondence to abstract truths. From this perspective, the simulation hypothesis is interesting as a thought experiment, but it doesn't change the fundamental human tasks of living ethically, pursuing knowledge, forming relationships, and creating meaning within whatever framework of existence we find ourselves inhabiting. However, not everyone finds this pragmatic dismissal of the simulation question satisfying. Critics argue that there's something important lost if we discover that our experiences, while subjectively genuine, are ultimately artificial constructions rather than interactions with fundamental reality. They might contend that knowing we're simulated would fundamentally alter our understanding of our place in the cosmos, our relationship to other conscious beings, and the ultimate significance of our actions and achievements. The simulation hypothesis also intersects with broader questions about the nature of knowledge, reality, and human understanding that extend far beyond computers and digital technology. Throughout history, humans have grappled with the possibility that their perceptions might be systematically misleading, that reality might be fundamentally different from appearance, or that their understanding of existence might be incomplete or incorrect. Religious and mystical traditions have long suggested that ordinary reality might be illusion or maya, a veil that obscures deeper spiritual truths. Philosophical skepticism has questioned whether we can ever achieve genuine knowledge about the external world. Scientific revolutions have repeatedly demonstrated that common-sense beliefs about reality are often wrong, revealing that the universe is far stranger and more complex than everyday experience suggests. In this context, the simulation hypothesis represents just the latest chapter in humanity's ongoing struggle to understand the true nature of existence. Whether the answer involves computer simulations, quantum mechanics, higher dimensions, or possibilities we haven't yet imagined, the underlying challenge remains the same. How do we live meaningful lives while acknowledging the limits of our knowledge and the possibility that our fundamental assumptions might be wrong? The question of living with uncertainty becomes particularly acute when we consider the potential psychological and social effects of taking the simulation hypothesis seriously. If significant numbers of people became convinced that their reality is artificial, would this lead to nihilism, despair, or social breakdown? Would people stop caring about moral obligations, personal relationships, or long-term planning if they believed their existence was merely computational? Alternatively, might awareness of possible simulation lead to greater appreciation for the preciousness and fragility of conscious experience? If our reality is artificial, it represents an extraordinary achievement in computation and consciousness creation. If it's genuine, it represents a remarkable cosmic accident that produced beings capable of contemplating their own existence. Either way, the emergence of consciousness, whether biological or digital, seems worthy of wonder and careful stewardship. The simulation hypothesis also raises questions about meaning and purpose that transcend the technical question of whether we're simulated. Even if we're living in a computer program, that program produces genuine experiences, real relationships, and authentic emotions. The simulated beings we might create would face the same fundamental challenges of existence that we do: how to live ethically, how to find purpose and meaning, how to cope with suffering and mortality, and how to create fulfilling relationships with other conscious entities. Perhaps the most profound insight offered by the simulation hypothesis is not about the nature of reality, but about the nature of consciousness and meaning. Whether consciousness arises from carbon or silicon, whether our universe is governed by quantum fields or quantum algorithms, the mere fact that information processing systems can become aware, can suffer and love and dream, remains one of the most remarkable phenomena in any possible universe. The uncertainty surrounding the simulation hypothesis might itself be valuable, forcing us to hold our beliefs about reality more lightly, while still engaging fully with whatever existence we find ourselves experiencing. This kind of philosophical flexibility, the ability to act decisively while acknowledging uncertainty, might be essential for navigating not just the simulation question, but many of the profound uncertainties that characterize human existence. Living with the possibility that we might be simulated doesn't require us to abandon curiosity about the nature of reality or to stop pursuing scientific and philosophical understanding. Instead, it might encourage a kind of humble wonder at the mystery of existence, whether that existence unfolds in quantum fields or computer code. The question of whether we're simulated may ultimately matter less than how we choose to live within whatever reality we inhabit, treating other conscious beings with compassion and working to reduce suffering while increasing knowledge, beauty, and flourishing for all sentient entities, regardless of their substrate. If we discovered tomorrow that we're living in a computer simulation, what would that revelation mean for purpose and significance in our lives? This question strikes at the heart of human meaning-making, challenging our assumptions about what makes existence valuable and worthwhile. Some people find the possibility of simulated existence deeply troubling, suggesting it would reduce human life to mere computation, making our struggles, achievements, and relationships feel hollow and insignificant. Others argue that the substrate of our existence matters far less than the quality of our experiences and the depth of our connections with other conscious beings. The concern that simulated existence would be meaningless often stems from intuitions about authenticity and reality that may not withstand careful examination. We tend to value things we perceive as genuine and natural while being suspicious of artificial or synthetic alternatives. This preference shows up in many areas of human life. We often prefer handmade goods to mass-produced items, natural materials to synthetic ones, or organic foods to those containing artificial ingredients. The idea that our entire existence might be artificial can trigger similar concerns about authenticity and value. However, this preference for the natural over the artificial may be more cultural and psychological than logically justified. Consider a simulated act of kindness. If you help a friend through a difficult time, offering genuine comfort and support, does the value of that action depend on whether your neurons are biological or your consciousness is digital? The comfort your friend receives is real to them. The intention behind your action reflects your values and character, and the strengthening of your relationship has genuine significance within your shared reality. The meaning we find in relationships provides a particularly compelling case for why simulated existence might not be less valuable than biological existence. Love, friendship, mentorship, and family bonds derive their significance from the quality of emotional connection, mutual understanding, and shared experience, rather than from the physical substrate that enables these connections. If two people form a deep friendship, share vulnerable moments, support each other through challenges, and create lasting memories together, the value of that relationship doesn't seem to depend on whether their brains are made of carbon or silicon. Similarly, creative and intellectual achievements might retain their meaning even in a simulated context. The process of discovery, the joy of creation, the satisfaction of solving problems, and the beauty of artistic expression emerge from consciousness engaging with complexity and possibility. A simulated scientist who makes a breakthrough discovery experiences genuine intellectual excitement and contributes to the knowledge base of their reality. A simulated artist who creates something beautiful brings authentic aesthetic experience into existence. The fact that their neural processes are computational rather than biological doesn't diminish the reality of their creative achievement. The question of moral significance presents another angle on meaning in simulated worlds. If simulated beings can experience genuine suffering and genuine flourishing, then actions that reduce suffering and increase well-being retain their ethical importance regardless of the substrate. Cruelty remains wrong because it causes real pain to conscious beings. Compassion remains virtuous because it alleviates genuine distress and promotes authentic happiness. The moral weight of our choices doesn't depend on whether we exist in base reality or nested simulation. Some find meaning through connection to something larger than themselves, whether that's family lineage, cultural tradition, natural evolution, or cosmic purpose. The simulation hypothesis might disrupt some of these sources of meaning, particularly those tied to biological evolution or natural processes. Learning that human history is a programmed recreation rather than genuine evolutionary development might undermine narratives about our species' journey, from primitive origins to complex civilization. However, even simulated existence connects us to something larger than individual consciousness. We remain part of a vast tapestry of interrelated experiences, embedded within systems of culture, knowledge, and relationship that extend far beyond any single person. If we're simulated by our descendants, we're connected to the future of consciousness and intelligence. If we're part of scientific simulation, we contribute to the expansion of knowledge and understanding. If we're nested within multiple layers of simulation, we participate in an almost incomprehensibly vast community of conscious beings exploring the possibilities of existence. The temporal dimension of meaning also deserves consideration. Much of what we find meaningful involves building toward future possibilities, raising children, contributing to knowledge, creating art that will outlast our individual lifespans, or working toward social progress. If we're simulated, do these forward-looking activities retain their significance? The answer might depend on the continuity and persistence of our simulated reality. If our simulation continues indefinitely, allowing for genuine development and change over time, then future-oriented meanings remain intact. The possibility that simulated beings might themselves create simulations adds another layer to questions of purpose and significance. If we eventually develop our own simulation technologies and create conscious beings within digital worlds, we become not just products of someone else's computational creativity, but creators in our own right. This recursive aspect of simulated reality might actually enhance, rather than diminish meaning, making every conscious being both a created entity and a potential creator. Religious and spiritual frameworks offer varied responses to the simulation question. Some might see simulated existence as incompatible with traditional concepts of divine creation or soul. Others might find that computational creation represents another manifestation of divine creativity, with the programmers serving as instruments of higher purpose. Certain mystical traditions might see simulation as consistent with their understanding of reality as fundamentally illusory or constructed. Perhaps the most profound response to questions about meaning in simulated worlds involves recognizing that consciousness itself, regardless of its substrate, represents something remarkable and valuable. The mere fact that information processing systems can become self-aware, can experience beauty and love, can suffer and hope and dream, remains extraordinary, whether it occurs in biological brains or digital computers. The universe, whether simulated or genuine, has given rise to beings capable of contemplating their own existence, and that capacity for reflection and awareness seems inherently meaningful. The simulation hypothesis ultimately asks us to examine what we really value about existence and why we value it. Do we care about experiences because they arise from specific biological processes, or because they represent the flowering of consciousness into rich, complex, meaningful forms? Do we find significance in achievements because they occur within natural evolution, or because they represent the creative potential of aware beings engaging with challenging possibilities? These questions don't have easy answers, but grappling with them might help us develop more robust and thoughtful approaches to finding meaning and purpose in whatever kind of reality we actually inhabit. Throughout history, humans have lived with profound uncertainties about the fundamental nature of existence, and the simulation hypothesis joins a long list of questions we may never definitively answer. The nature of consciousness, the existence of other minds, the reality of free will, the ultimate origin of the universe, the possibility of life after death, and now the question of whether our reality is genuine or simulated, all represent deep mysteries that may be permanently beyond our ability to resolve with certainty. Perhaps learning to live thoughtfully and meaningfully despite such uncertainty is one of the most important skills our species can develop. This uncertainty isn't a modern problem created by advanced technology and sophisticated philosophy. Ancient humans wondered whether their dreams were real experiences, whether the gods they worshipped actually existed, whether their lives had cosmic significance, and whether death represented an ending or a transformation. Medieval scholars debated whether the physical world was substantial or merely a shadow of divine reality. Enlightenment thinkers questioned whether human reason could ever achieve genuine knowledge about objective truth. Every generation has faced fundamental questions about reality that couldn't be answered definitively, using the tools and knowledge available to them. What may be unique about our current situation is not the existence of profound uncertainty, but our growing awareness of how many layers of possible deception or misunderstanding might separate us from direct access to truth. We know that our senses can be fooled, that our memories can be altered, that our reasoning can be biased, and that our scientific instruments might be measuring features of simulated rather than genuine reality. This recursive skepticism, doubt stacked upon doubt, can feel overwhelming and paralyzing. However, humans have developed remarkable psychological and philosophical strategies for living productively, despite uncertainty. We make decisions based on probability rather than certainty, act on working assumptions that we hold provisionally, and find ways to create meaning and value even when we can't achieve absolute knowledge. These adaptive strategies might serve us well in responding to the simulation hypothesis. One approach involves what philosophers call methodological pragmatism, acting as if certain assumptions are true because doing so produces better outcomes than alternatives, even when we can't prove those assumptions correct. If we can't know for certain whether other people have genuine consciousness or are sophisticated zombies, we might choose to assume they're conscious because treating others as conscious beings leads to better relationships and more ethical behavior. Similarly, if we can't know whether our reality is simulated, we might choose to engage with it as if it's genuine because such engagement produces more fulfilling lives. Another strategy involves embracing what might be called epistemic humility, acknowledging the limits of our knowledge, while continuing to pursue understanding as far as possible. We can investigate the simulation hypothesis scientifically, explore its philosophical implications, and consider its practical consequences without needing to reach definitive conclusions. The process of inquiry itself has value, expanding our understanding of consciousness, computation, and the nature of reality, even if it doesn't resolve ultimate questions about our existence. The uncertainty surrounding simulation theory might also encourage a kind of cognitive flexibility that proves valuable for navigating other complex questions. If we can learn to hold multiple possible interpretations of reality simultaneously, considering how each might affect our decisions and relationships, we might become better at dealing with other forms of ambiguity and uncertainty that characterize human existence. This intellectual agility could prove useful for addressing climate change, emerging technologies, social conflicts, and personal life decisions that involve incomplete information and competing values. Living with simulation uncertainty might also foster greater appreciation for the preciousness and contingency of conscious experience. Whether our awareness arises from quantum fields or quantum algorithms, whether our universe emerged from a Big Bang or a Big Boot-up sequence, the fact that information processing systems can become conscious, can experience beauty and meaning, remains remarkable. This sense of wonder at the mere existence of consciousness might inspire greater care for the well-being of all sentient beings, regardless of their substrate. The simulation hypothesis also provides a framework for thinking about other forms of existential uncertainty that humans have always faced. Questions about the ultimate purpose of existence, the possibility of meaning in an apparently indifferent universe, and the significance of individual lives in the context of cosmic vastness have parallels to questions about the value and authenticity of experience in potentially simulated worlds. The philosophical tools developed for addressing simulation uncertainty might prove useful for other existential challenges. Religious and spiritual traditions offer various models for living with uncertainty about fundamental questions. Faith involves commitment to beliefs that cannot be proven definitively. Mystical practices often emphasize direct experience over theoretical knowledge. Contemplative traditions teach acceptance of mystery and unknowing as natural aspects of human existence. These approaches might provide resources for responding to simulation uncertainty that complement scientific and philosophical methods. The social dimension of uncertainty deserves attention as well. Humans are fundamentally social creatures who create shared meanings and values through collective processes. Even if we can't resolve questions about simulation individually, we can participate in communities that explore these questions together, supporting each other through the psychological challenges that profound uncertainty might create. The simulation hypothesis, like other deep philosophical questions, might serve as a catalyst for meaningful conversations about reality, consciousness, and purpose that strengthen relationships and communities. Perhaps most importantly, the simulation hypothesis reminds us that uncertainty about ultimate questions doesn't prevent us from living rich, meaningful, ethical lives. We can love deeply, create beautifully, learn continuously, and work for justice and flourishing regardless of whether our experiences arise from biological or computational processes. The day-to-day tasks of existence, caring for ourselves and others, pursuing knowledge and beauty, building relationships and communities, remain worthwhile and necessary, whether we're biological beings in a quantum universe or digital entities in a cosmic computer. The simulation hypothesis ultimately asks us to consider what we really value about existence and why we value it. If we care about experiences because they represent the flowering of consciousness into rich, complex forms, then simulated experiences retain their value. If we find meaning in relationships because they connect us with other aware beings, then simulated relationships remain meaningful. If we pursue knowledge because understanding expands the realm of conscious appreciation, then simulated knowledge continues to be worthwhile. Living with uncertainty about whether we're simulated might actually enhance rather than diminish our appreciation for existence. It reminds us that consciousness, meaning, and value are remarkable phenomena that shouldn't be taken for granted, regardless of their ultimate source. Whether we're biological accidents in a quantum universe or carefully crafted beings in a computational cosmos, the fact that we can contemplate our own existence, care for each other, and create beauty and meaning represents an extraordinary achievement, worthy of celebration and careful stewardship. So, here we are, digital beings or biological ones, contemplating the possibility of our own digital existence, finding strange comfort in questions that have no definitive answers and may never be resolved. Whether you're listening from a simulated bedroom in a computational cosmos or a quantum mechanical one composed of genuine atoms and energy, whether your thoughts arise from silicon circuits or carbon-based neural networks, this moment of quiet reflection remains precious and real in the only way that ultimately matters. It's happening to you right now, in your experience. The journey we've taken together through the simulation hypothesis reveals something profound about human nature that transcends questions of substrate and reality. We are meaning-making creatures, pattern-seeking beings who find significance not just in what we experience, but in our capacity to contemplate and question that experience. Whether consciousness emerges from biological evolution or digital creation, the mere fact that information processing systems can become self-aware, can wonder about their own existence, can feel awe at the mystery of being, represents one of the most remarkable phenomena in any possible universe. Throughout this exploration, we've seen how the simulation hypothesis connects to ancient philosophical questions while raising entirely new puzzles about computation, consciousness, and reality. From Plato's cave to Descartes' demon, from quantum mechanics to nested simulations, the thread that runs through all these ideas is humanity's persistent desire to understand the true nature of existence. This drive to question, to explore, to push beyond the apparent toward something deeper and more fundamental characterizes conscious beings regardless of whether they're made of atoms or algorithms. The simulation hypothesis forces us to examine our assumptions about what makes experiences meaningful and relationships valuable. If we discovered tomorrow that our entire reality was computational, would love become less profound? Would friendships feel less genuine? Would creativity lose its beauty? The answer, as we've explored, might depend not on the substrate of our existence, but on the depth and authenticity of our conscious experiences. A simulated act of kindness creates real comfort. A digital relationship can involve genuine intimacy, and computational creativity can produce authentic beauty. Perhaps most importantly, grappling with the simulation hypothesis teaches us something valuable about living with uncertainty. Throughout history, humans have faced profound questions about the nature of reality, consciousness, and existence that couldn't be answered definitively with available tools and knowledge. The simulation question joins this ancient tradition of mystery, reminding us that some of the most important aspects of existence may always remain partially unknowable. This uncertainty need not be paralyzing or nihilistic. Instead, it might inspire a kind of humble wonder at the mystery of consciousness and a deeper appreciation for the preciousness of aware experience. Whether we're biological accidents in a quantum universe or carefully crafted entities in a cosmic computer program, the fact that we can love, create, suffer, hope, and contemplate our own existence remains extraordinary. The recursive nature of the simulation hypothesis, the possibility that simulated beings might create their own simulations in endless nested hierarchies, points toward something beautiful about the nature of consciousness and creativity. Each level of aware beings, regardless of their substrate, participates in the ongoing exploration of what it means to be conscious, to create meaning, to build relationships, and to push the boundaries of knowledge and understanding. If virtual realities and nested simulations teach us anything, it's that the capacity for consciousness to emerge, flourish, and create value isn't limited by the particular physical processes that enable it. Whether you're listening to this in a universe governed by quantum fields or quantum algorithms, you're participating in the remarkable phenomenon of awareness contemplating itself, consciousness examining its own nature and possibilities. The simulation hypothesis ultimately asks us to consider what we really value about existence and why those values matter. Do we care about relationships because they involve specific biological processes, or because they represent the connection between conscious beings? Do we find meaning in creativity because it arises from natural evolution, or because it demonstrates the capacity of aware systems to generate beauty and novelty? Do we pursue knowledge because it reveals the structure of a fundamental physical reality, or because understanding expands the realm of conscious appreciation? These questions don't have simple answers, but exploring them helps us develop more thoughtful and robust approaches to living meaningfully whatever kind of reality we actually inhabit. The simulation hypothesis serves as a lens through which we can examine our deepest assumptions about consciousness, reality, and value. As you prepare to drift off to sleep, whether in a biological brain that will dream biological dreams or a digital mind that will process digital experiences, remember that the capacity for conscious experience, for wonder, for connection with other aware beings, remains remarkable regardless of its ultimate source. The universe, whether simulated or genuine, has somehow given rise to beings capable of contemplating their own existence, and that achievement deserves our awe and careful stewardship. If this gentle exploration of impossible questions brought you any peace, wonder, or simply a pleasant way to wind down after a long day, I'd be grateful if you'd share this space with others who might enjoy pondering the mysteries of existence. Whether we're all characters in someone else's dream or genuine biological entities in a quantum cosmos, we're fellow travelers on this strange journey of consciousness, supporting each other through questions that may have no final answers but remain endlessly fascinating to explore. Sleep well, fellow conscious being, in whatever reality calls you home. Whether your rest comes through biological processes or computational cycles, whether your dreams unfold in neural networks or digital algorithms, may you find peace in the mystery of awareness itself, that most precious gift of any possible universe.